Deep or deep learning accelerator based on a streaming architecture for binary neural networks. Abstract. Deep neural networks, DNNs, have played an increasingly important role in various areas such as computer vision and voice recognition, while training and validation become gradually feasible with high-end and general-purpose processors such as graphical processor unit (GPU), high-throughput inferences in embedded hardware platform with low hardware resources and low consumption efficiency are still challenging. Binarized neural network (BNNs) are emerging as a promising method to overcome these challenges by reducing width of DNN data representations with many optimal prior solutions. However, accuracy degradation is a considerable problem of BNN compared to the same architecture with full precision, while the binary neural networks will contain significant redundancy for optimization. In this paper, to address the limitation, we implement a streaming accelerator architecture with three optimization techniques. The pipelining unrolling for streaming each layer will weightily used for parallel computation, and the MAC multiplication accumulation compression. Our method first constructs streaming architecture by pipelining unrolling method to optimize the throughput. Next, the weighted reuse method with the k-mean cluster is applied to reduce the complexity of the pop count operation. Finally, MAC compression reduces hardware resources used for remaining computation on MAC operations. The implementation hardware accelerator integrated into a state-of-the-art field programmable gate array (FPGAs) provided the maximum performance of the classification at 1,531 kiloframes per second with 98.4% accuracy for the MNIST dataset and 205 kiloframes per second with 80.2% accuracy for the Cipher 10 dataset. Besides, the proposed design ratio FCS and LUTs is approximately 57 MNIST and 0.707 Cipher 10, which is much lower than the state-of-the-art design with the comparable throughput and inference accuracy. Introduction. In recent years, the machine learning has become a popular terminology because of its applicability in a variety of fields. Particularly, deep neural network (DNNs) have shown remarkable ability in classification tasks with a high accuracy, such as computer vision and speech recognition. To adapt to more applications with more enormous datasets that need to have higher accuracy, researchers have tended to devise deeper networks that contain more parameter layers with bigger model sizes. More complex DNNs directly affect power, resource efficiency, and throughput as many computation and many requirements for model parameter storage increase. Notably, in a design implementation in FPGA or ASIC, a more significant number of logic gates are required to handle the increased number of operations that consequently incur higher energy consumption and lower processing performance during runtime. Meanwhile, data required for most of the larger DNNs may not be entirely stored in on-chip RAMs, which result in off-chip DRAM access. This alternative becomes undesirable since data transfer consumes significant energy and lowers processing performance. Researchers have proposed many optimized strategies to improve the DNS performance, and one among several approaches was to reduce calculation precision, which was proven to contain potential redundant information. Following one of the publications focusing on a precision reduction in 2016, Covario et al. Proposed a binary training method that produced BNNs giving the best accuracy on most popular datasets. This approach was rapidly deployed on most state-of-the-art network models because of its feasibility in addressing challenging above. With binary precision, memory size was considerably reduced while all publications are replaced by X and XNOR functions, which can dramatically shrink the computational size and save a vast amount of the energy. In addition, to further improve the design's quality in 9 to 12, the authors proposed other optimization technique to reduce computation on batch genome, pulling the adder tree operation by using the threshold comparison or gate or logic gates and counting one values respectively. Recently, two approaches have been used to deploy DNS on the hardware implementation, including PNNs. The first single-area architecture in which one hardware block processes the network layer by layer, one at a time. In particular, the design with this architecture is used to perform the computation for all layers with the same shape at different times. Hence, after loading a specific number of input pixels, the next layer has to wait for the previous layer to finish before execution. Consequently, the hardware design needs to postpone loading new input pixel to process to loaded data. When increasing the number of layers, the total waiting time between two loaded input and images increases, causing the throughput to be down. Regarding BNNs, most previous designs were implemented with this architecture. In addition to the independent optimization for every BNNs, as you mentioned above, to optimize for only single-layer architecture when applying to the BNN models. Variable with line buffer or sliding window unit were proposed to provide input data computation effectively. Especially, Chang Fu et al. Proposed a way to reuse and input reuse method that can reduce a considerable amount of computation on popcorn operation based on the similarity among lists of parameters or input pixels. In general, a single-layer architecture would be the best option for enormous models with limited resources devices. However, for the BNN implementation, this architecture may not utilize the full advantages of BNNs to enhance the high throughput, resources, and power efficiency compared to the streaming architecture's second approach. More specifically, in a streaming architecture, because the whole network of a BNN model is fully implemented, computation on all layers is simultaneously performed, leading to the high utilization. Moreover, the architecture is streaming, while the input is images, the output is the classification result, and no residual connection exists. Hence, input pixels are regularly loaded into the design without interruption. After a specific latency, the classification result is generated with a constant speed regardless of how many layers. In consequence, the throughput is significantly improved compared to the single-layer architecture. On the other hand, the one BNN optimization with the streaming architecture. The BNN design can further optimize by replacing the XNOR logic gate with NOT gates or directly connecting to the output. In doing so, the memory used to store parameters is eliminated, resulting in an energy reduction for data delivery. In addition to compared to the single-layer architecture, another streaming architectural advantage is that a processed data is directly delivered from the previous to the next layer without any intermediate buffer or memory. However, the development cost and flexibility may make implementation for the streaming architecture challenging, even impossible, especially for the convenient neural network. In BNN, although these problems become less critical when the corner and feature maps precision is reduced to 1, they are still drawbacks for big model sizes. And this paper to tackle mentioned the problem and maintain the advantage from this kind of architecture. We target successfully implementing a streaming BNN hardware architecture on FPGA devices with a high throughput, the best power and area efficiency based on a ratio FPS, frame per sec, and power and PFS LUTs. The main features of the proposed architecture are as follows. 1. An efficiency pipeline and lowering mechanism that maximizes the utilization of all layers. 2. A combination of weighted reuse method and k-mean, called MAC optimization, is applied to the both convolutional and fully connected layers to reduce the complexity of pop count operations. 3. A MAC compression method that compresses the pop count tree with two options for adders, 6-bit adder and 3-bit adder compressor without accuracy impact. Besides, the method allows more than one output channel to use the same pop count operation, which helps the design considerably reduce the resources energy, especially for large models. 4. An automated hardware implementation flow for the proposed accelerator that helps users facilitate the hardware implementation for different topologies. Compared to the previous work in N18, the proposed design, a streaming architecture consumed more resources for the same BNN models. However, the practical application impact on the area issue in the proposed design are minimized via the above compression techniques. Meanwhile, with the advantage of the streaming characters, the proposed design provides better throughput, utilization, and efficiency in resources and in energy. Especially, it is not as in the 18. In the proposed design with the combination of k-means cluster, the weighted reuse method is directly applied to without any additional resources and effect on the throughput latency. This architecture capability is demonstrated by using the MNIST and the CIFAR-10 benchmark test set. Compared to the previous best published result, our proposed architecture consumed 3 times fewer LUTs and eliminated FPGA block RAM and DSP while producing approximately the same FCS with the same accuracy. This is the BNN hardware architecture with the highest power and area efficiency and acceptable late accuracy to the best of our knowledge. The rest of the paper is organized as follows. Section 2 introduces a common background related to the BNN and the theoretical method to use to optimize the BNN hardware implementation. Section 3 describes our proposed architecture, the process of generating artificial design, experimental result, and the comparison among our design and the other papers are presented in Section 4. Finally, the conclusion is the last section. Back to background A, binary neural network. According to the 7, BNN is also a type of a neural network in which both weight and activation outputs are constrained to -1 to +1 for negative and positive values respectively. To transform the real variable to these values, they used two different binarization functions. Firstly, the deterministic function is like this. Secondly, a stochastic function like this, expression 2, where the x 0 mean this expression, and the x the power of the b is the output of the function after binarizing. The deterministic function is mainly used for practical hardware implementation, while the stochastic function also can be used in BNN. Using the above binary functions, all the weights and the outputs of the both convolution and fully connected layers are reduced to a single bit before being used in the subsequent operations. Therefore, all the hardware consuming the multiplications can be replaced with XNOR logic. The other tree used in the follow-up of the accumulation is also significantly simplified with the pop count operation as described in figure 1, even though the multiply accumulate MAC operation holds the most neural net workload. Optimizing other cheaper operations such as a batch norm and a max pool can still benefit the BNN performance. The applied technique for each type of the operation are described in the following subsection. 1. Batch norm operation is BNN. Unlike the MAC operation, the batch norm function uses the floating point parameters and the complicated calculations, and including division, root square, and multiplication. As usual, the batch normalized value of the x is calculated as, and in which the epsilon is a small number of avoided round-off problems. Micro and variable is a mean, and the variance of the trained data is batch gamma and beta are constant learned from the training process. The normalized value is then binarized as like this, and the two steps of normalizing and binarizing they can be combined into much simpler threshold comparison as following. If, like this, the final formula can be described. Hence, in the hardware implementation, a combination of the batch norm and binarization is now on output of the comparison of a successive XNOR gate. 2. Max pool operation in BNN. In BNN, after the batch norm operation, some layers use the max pooling operation to reduce the input activation for successive layers. Theoretically, the output of the max pooling operation is binarized before being transferred to the next layer. By swapping the binarization and the max pooling and the module, the batch norm and the binary function can be combined while retaining the output reserve. In addition, the computing max values of a binary window is the same as the final output of the OR operation with the binary value inputs. Eventually, there is a serial combination starting from the batch norm to the OR operation as shown in figure 2. From a hardware implementation point of view, the OR operation is simpler than the max operation in non-binary neural networks. Weight reuse method. As mentioned above, the BNN's emergency with its particular characteristics has been considered as a promising solution in minimizing hardware resource and power consumption. In particular, the 1-bit with the BNN models has been effectively utilized to maximize the parallel level of the data process and reduce computation effort by the XNOR logic gate and the pop count operation. However, if we analyze the pattern of the weight values, the current BNN models still have a considerable amount of redundancy requiring further optimization. Because of this, some computational operation and memory resources can be saved. As As introduced in 18, a binary number is used to express two states, 1 and 0 and 1. Hence, when I pick a random binary number, the probability of 0 or 1 is the same as the 50%. If we have two random sets of them binary bits, we assume that we need more than a k bit repeated on the second bit set compared to the first n bit set. First n bits. Thus, the probability happening this expectation is as the following equation. For example, if we need more n over 2 bits repeated in the second bit that is n even, like this, if the k is smaller than n over 2 and divided by 2, n over 2, we can get a large probability. Therefore, the number of bits can on the first set repeated respectively on the second set would be considerable for binary conversion layer. To calculate k output channels, each bit in a set of the bit values m times c, binary bits XNORs with the corresponding bit in a k different sets of the m by n times m by the c binary corners values in which m is the size, c the number of input channels. Consequently, the number of similar bits between the two arbitrary sets of the corner bits is considerable. To take this advantage of conventional binary convolution for optimization in 18, Cheng Fu et al. Proposed a weight reuse method. This method executes calculating on an output channel by implementing entire XNORs and a pop count operation for the corresponding set of n times m times c binary weight values by the against uses this amount to calculate the other output. To be easier in visualizing and described in more detail in subsection with accompanying formula, we assume that there are n different bits between m and c binary corner bit set, a for the first corner set and b for second corner set. So ai not bi for all I from n1 to n, call x as a unknown input feature map set in which correspond to the n different bits of the two binary corner bit set. When we execute the XNOR one random with 1 and or then 0, then the sum these outputs a final result is always 1. Generating for n random bits, we have the following equation. The left C corner bits on two corner sets are the same. Thus, the pop count output of the AC XNOR X can be calculated as the following. For popcorn output is a BC XNOR X based on P1, we can transfer as following. Finally, we have the equation using to calculate the P2 based on the P1 as the following. According to the 12, the output of the second channel is like this, and in this case, P2 is calculated as equation 8. Thus, the final output is described as like the expression 9. Equation 9. There is a quite familiar feature for the first convolution layer, which uses full precision input pixels. In doing so, the result is 0 for the sum of the two multiplications, ax minus 1 and ax. A is an arbitrary full precision pixel. So regard the number of the different bits between the two sets of corner bits and the sum of the multiplication between the arbitrary full precision input pixels and corresponding the different bits of the second channel at D and at S2 respectively. We can calculate the output of the second channel as the following equation. Equation 10. In this way, we do not need to implement a whole convolution operation which leads to a considerable hardware resource reduction while guaranteeing output accuracy. 3. The proposed architecture. A high-level streaming architecture. Figure 3 shows a generic high-level system architecture of the proposed BNN architecture. The BNN design is connected to the DDR memory via directed memory access DMA IP using the AXI4 stream bus. Two fixed memory areas are used to store input images and output classification from BNN design in the DDR memory. The DMA block provides the initial configuration, start address, and the data length of these two memory areas. Each input pixel from the input memory area is sequentially delivered to the streaming BNN architecture. After a particular latency, output classification is back to the second DDR memory area, depending on the design or loading levels, which would discuss the next section. The bandwidth of a streaming data bus can be changed to satisfy the requirement. In contrast with a single-layer accelerator, where a single hardware accelerator processes a neural network layer by layer sequentially. At the coarse grain level, we proposed a multiple-layer streaming architecture which implemented the whole network architecture on a hardware implementation. In particular, as the idea is in a proposed Kim et al. On the Boltzmann machine ANN, the streaming architecture in this paper is implemented in a coarse grain pipeline manner. This approach is achieved via dividing an interface workload into a layer granularity, and in which the number of the pipelining stages is equal to the number of the layers. This way, input pixels are received continuously and every layer can be simultaneously proposed, resulting in the highest performance. Additionally, because of the output of a previous layer is directly delivered to the next, without any intermediate storage, the proposed accelerator can mitigate propagation delay and reduce a significant amount of the memory. On the other hand, since all layers are fully implemented and the input data is continually processed, increasing the number of layers causes a longer initial latency. It does not affect the throughout of the steady-state system time. For example, suppose the dimension of the primary input from frame is EXF, E times F or EFX, and the input data is delivered to the design every clock cycles. In that case, the accelerator requires E asterisk F clock cycles to classify the frame after the initial filling time. Consequently, the throughput of the design can be flexibly changed based on the number of input pixels loaded into design and each clock cycle. In detail, each layer is also constructed under the pipelining technique. The convolution layer is divided into four more minor phases. The first phase is a multiplication operation. The second phase is a pop count. The third phase is normalization. And the final phase is binarizing. The next is the filling layer. The data from the binarizing phase can be delivered directly into the pooling process. Figure 4. Full conventional pooling layers. In particular, as shown in Figure 4, a comprehensive layer including the convolution, line buffer, multiplication pop count, metronome, and a pooling layer is described. This proposed architecture is a complete binary combination of a typical convolution of the pooling layers. And doing so, we need to store threshold value for a metronome operation. Meanwhile, the memory used for storing weight values and the sign of the metronome operation is totally removed. Hence, the working process is enabled without delay in the parameter delivery. Firstly, to finish the process from the input to the output of a layer, input pixels from the previous layer are carried to the convolution line buffer. When a specific number of the input data are loaded into a line buffer, all window values generated and shifted into the W times WB block as input of the multiplication pop count module. Output values from the count Wx, W times Wb block are compared with the threshold parameter at the batch norm block. Then they are processed with a suitable operation depending on the sign of the batch rate, which is detailed in subsection B. Finally, there is no pooling layer. Outputs of the batch run are directly carried to the next convolution layer. By contrast, data is pushed into the pooling line buffer. When the number of values loaded into the line buffer reaches the acceptable condition described in the following section, output windows are produced, data is transferred and delivered to the next layer through the OR operations. B. Microarchitecture for window generation into convolution and the pooling layer. Thus, this subsection describes the detail of the convolution and the pooling layer architecture, in addition to the efficiency of the combination among the pipeline, unloading method, and a pop count optimization. Each layer is mentioned as well. The figure 5, a genetic convolution between the C and Windows M by M and A K times C times M times M filters. To facilitate this explanation as shown in the figure 5, we regard EXF, E times X, as the dimension of the input feature map, M times M as the dimension of the features, C as the number of the input channels, and K as the number of the output channels. As we know, in convolution, windows including the input feature map data into X times M are multiplied by corresponding features with the same size before the adder tree, in which M is 3 in a proposed design. On the other hand, in pooling layers, pooling window with windows size data with size 2 by 2 are also needed to be provided for pooling process. To provide this window for next processing, we design a lightweight shift register-based line buffer to store only the needed data streaming from the previous layer. In this layer, the hardware implementation for a specific layer only waits for the necessary input data to start each operation instead of waiting till the previous layer ultimately to produce the complete feature map. Besides, each layer does not need to wait to complete the previous layer. Layer level pipeline stages can be overlaid, thus significantly reducing the initial pipeline filling time. Algorithm 1 is convolutional line buffer pseudocode. So in particular, two types of line buffers are implemented in the proposed accelerator: convolution line buffer and pooling line buffer. First, the CLB stores a specific number of input cells from the previous layer and sequentially provide a convolution window multiplication operation. Usually, CLP includes M-1 times E plus M pipeline register in the number of register windows is only 1. Meanwhile, as shown in figure 6, the size of a CLB M-1 multiply E times E plus M plus N minus 1 if the number of the generated parallel windows increases to N every clock cycles. In this multiplication, pop count processes the number of the calculation would be n times of generating on one window. In terms of working mechanism, and the number of field register in the CLB is equal to, and the CLB starting selecting the appropriate value for the output value by their coordinating on the CLB and the feature map, then the pops them out of the simultaneous assert the corresponding are valid for the case n plus n is larger than 1. The CLB needs to be received and input values continuously with the same period generate and windows continuously for each cycle clock. If the input is the value from the previous layer, which is also received, and input values requirement would be solved. All layers would eliminate the issue for the first convolution layer if the memory can provide n with n input values at each clock cycle. The details process is illustrated in algorithm 1 with the following notation. Rx, Ry is the coordinate of the center of the window, the frame. Ix, Iy is coordinate of each pixel on the window, and L is a convolutional line proper with the length m minus 1 times E plus m plus n minus 1. In order to make algorithm 1 clearer, the paper provides a visual description about the line buffer situation when the CLB starts generating the output with one window, figure 7, and when the CLB is at the middle of the frame transmission, figure 8. Figure 8, figure 8, and the width M3 and the E and 528 for the MNIST dataset. E and FN32 for the CIFAR 10 dataset. The second type of the line buffer is pooling the line PLB, pooling line buffer PLB. The PLB is considered as the intermediate bridge between the batch genome and the pooling operation. Our data from the batch genome is gradually pushed into the PLB, while generated windows from the PLB are pushed into a pooling operation. Compared to the CLB and PLB does not consider the border padding, and the value signal is only asserted at the even position in the input frame map as shown in figure 9. Figure 9. Typically, the supposed window is 2 by 2 and the number of the window produced is 1. In that case, the visual signal is enabled after every 2 clock cycles for the first pooling layer, and after each 2i clock cycle of the 4ith pooling layer while satisfying the condition y modulo 2 is 0. To utilize the spare interval between the 2 times producing the windows of the PLB, the paper proposed generating windows from the PLB every clock cycle by increasing the parallel level of the input data. In particular, after the pooling layer is simultaneously provided, n input value n is greater than 1 and the power of 2 input values, and the number of generated parallel windows is n over 2. These area of the by these windows of this pooling layer will be answered producing every clock cycle when a y over 2 is 0. Therefore, the n parallel input values, the PLB can increase the speed of the n times y. The parallel of the level is only n over 2. This means the hardware source is responsible for the next multiplication. Pop count operation are used to reduce the half compared to the previous multiplication, the pop count operation. Regarding the PLB size, if the PLB outputs an overall window corresponding to n parallel input, the line buffer size E plus n register. Hence, depending on the number of parallel input values provided from the previous layer, the size of the PLB may n over 2 is greater than 1 or may not is n over 2 is 1. Need to increase when compared to the providing single input data. Besides, it is worth noting that a number of parallel input values must be a power of 2 and the divisor of E. For instance, if the pooling window size is 2 by 2 and the number of parallel inputs from the previous layer is n is equal to, then the PLB size E plus 2 registers and produces 1 pooling window for each clock cycle, yielding twice the output throughput. Compared to n equal n is while the previous layer provided n equal 4 parallel inputs, and the PLB size is plus 4 is registers and produced 2 windows after each clock cycle with 4 times the throughput n equal 1. In terms of the working mechanism, the PLB starts generating pooling window when the PLB is entirely filled by the valid data. In particular, the latency plus n over n clock cycles from the input value signal is asserted. The detailed process Sorry. The detailed process decrease in algorithm 2, accompanied by the figure 9 that shows the line buffers operation from the beginning to the end with the N1. C. Microarchitecture for MAC operation and batch norm. After the mentioned windows are generated by the lightweight fifth register-based line buffers, the data needs to go through a series of computations including the multiplication operation, pop count for the summation, and the batch norm normalization operation before the transferring to the next layer. At any degree of the parallelism, this process is already considered the stage causing the most critical timing path and assuming the most of energy in the design. This problem consequently leads to the limiting the operation clock frequency and the system throughput. In our architecture, all data paths of this process are managed at the highest level to mitigate this harmful influence, and every unnecessary computation is eliminating to avoid the processing delay the power consumption. Firstly, since all the weight of the value is constant and the multiplication operations, we can replace the XNOR and gate with the not gated when the weight value is 0 and directly connected the pop count when the weight value is 1. Similarly, in the batchroom operation, the sign values determine whether it uses the NOT gate or a NOT instead of the XNOR gate. In doing so, we reduce the considerable amount of latency by using the XNOR gate and also minimize the memory resources. Secondly, the parallelism pipeline technique and weighting reuse optimization implemented the proposed design to process binary neural networks efficiently. To facilitate how the method works in the design, the details are explicitly explained in the following. 1. Pipelining and parallelism mechanism. One factor that determined in the throughput of a processor is maximum clock frequency, while critical timing paths in the design limited the clock frequency. In the proposed BNN architecture, critical timing issues are in the paths from the matrix multiplication to the batch norm. However, these paths can easily be broken down into shorter paths by the adding intermediate registers. The system throughput can be significantly improved at the expense of the few initial latency cycles. Based on the required frequency, area, power, and the primary input number of channels and input bit width, we can locate registers to good points so that combinational logic delay paths become shorter than or equal to the target clock free period at the expense of the additional latency. In our experimental design, insert one pipelining stage to the output of multiplication operations among the pop count operation and at the output of the batch normal layer, which is described in figure 10. And regarding to the parallelism parallel techniques, massively parallel computing typically helps increase the total system throughput in the hardware implementation. However, the trade-off the considerable amount of the computing source hardware is needed and which leads to the higher power consumption and substantial fan-out increase congestion and may eventually render the design unroutable in BNN. Since the precision of the both weight and feature map data are reduced to the single bit, many loops in the convolution operation can be completely unrolled without massively increasing the hardware resource requirements while routing and congestion. Total 6 loops used in the convolution computation are described in figure 11. In this proposed design, we chose to unroll every inner loop from the third and loop in the sixth loop and operate optional long loop 2. Figure 2. Pseudocode with a total 6 loops in a convolution computation. Firstly, Unrolling loops 3 to 6 across all layers for a balance on the rate between the data consuming and producing in each layer accelerator. Hence, the technique allows them to operate continuously without idle time at the later layer or back pressure to the previous layer, regardless of the filter size of the number of colors in different layers. In particular, by rolling all these loops and open in all input windows generated from the line buffer on each layer executed simultaneously, leading to the significant propagation layer reduction. In addition to the loop 326, we also unroll the loop to investigate the hardware utilization among the different throughput requirements. Unrolling the loop 2 is achieved by increasing the number of generated windows from the line buffer each clock cycle and duplicating the computation MLC block sequence to the handle more especially location in parallel. That means that the all generating windows from the CLB are simultaneously executed through the corresponding sequence of the computation MX block. 2. MAC optimization. As mentioned in section 2, the weight of the reuse method is previewed to the substantially effective optimized pop count. And the figure 2 is a difference mechanism, the operations. In 18, Changfu et al. Utilized this method effectively by using the graph partitioning the finding Hamiltonian shortest path algorithm for each subgraph. For Hamiltonian shortest path, this is a good way to increase the number of weighted reduced operations. However, the convolutional layer, including the many channels, this technique may cause the number of the required flip-flops and latency to drastically increase if the method is applied to the streaming architectures. Typically, using the Hamilton paths makes each channel's output depending on the output of the previous channel, except for the first channel. Consequently, many registers must be added to be synchronized with the next layer, leading to the increased initial latency and hardware sources. For example, suppose the Hamiltonian graph is applied to the K output channel. In that case, the number of flip-flops which used to synchronize is blah 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 bandwidth, in which the M is the number of the output channels in calculated the same clock period, and the bandwidth is the data bandwidth used for the storing up pop count operations. The figure 12a describes clearly the problem. On the other hand, there is currently no practical algorithm to find the shortest Hamiltonian graph. Especially, it's more challenging if the number of vertices is considerable. For example, we seek the shortest Hamiltonian path for the connected to graph and with the m vertices. Recently, two approaches to have been applied to find the shortest Hamiltonian cycles, which can be used for the final shortest Hamiltonian path. And the first one is the exact solution, which can be used to find precisely the shortest Hamiltonian cycle by reducing the number of the searched Hamiltonian cycles. However, this approach will still take a long time and effort to calculate the final result, and especially with large graphs, typically when increasing the number of vertices, the processing times can increase exponentially with the branch and bound method in 12.6, or increase with a ratio n to n with dynamic programming method in 25. The second one is approximation algorithms being more common for massive graphs, but they have reduced poorer quality result than previous algorithms. To mitigate the above problem, the Changfu et al. Proposed a partitioning approach which split the whole graph into a specific number of the subgraphs in which the current number of the vertices of graph is limited to 64. However, this way increased the number of fully implemented output channels in hardware design. Besides, the number of subgraphs depending on the limited number of vertices in a subgraph, 64, to feasibly find the shortest Hamiltonian path. Hence, the more output channels, the more fully hardware implemented output channels that require more operations, resulting in the high hardware resources and power consumption. In this paper, we also set up a similar graph, which was set up m by n times m times c binary weight values represent the vertex and a number of difference between the two sets is considered the distance of the edge connecting two vertices. To partition the graph, we use K-means cluster algorithm to every R from the 1 to K. The number of output channels, 25. The optimal R values give us the smallest number of binary bits used to calculate the result for all output channels. That means all repeated binary bits compared to the corresponding centroid are eliminated. Figure 12b is an intuitive diagram describing the proposed method for a K-means cluster, and the following equation is the exact formula for finding the optimal R value, where R is the number of subgraphs, as Mi as the number of the vertices processing the same control centroid, and this I is the distance connecting the centroid I is the vertex J, and R times C times M times M is number total of the bits on R output channels which are fully implemented. This paper uses the K-means cluster to find the R groups of the vertices at their corresponding centroid. In theory, the output of the K-means cluster algorithm includes R subgraph and R corresponding centroid based on the R initial centroid and coordinated of the 2 or 4 vertices. So firstly, each vertex is clustered into a group where the distance from the vertex to group to centroid is shortest. In the second step, in each group of the vertices, the new centroid of this group is selected based on the following formula, blah blah, where the Mi and Xi are coordinates of the centroid and the vertex of the group respectively. These two steps are repeated until the sum of the all distances from the all vertices to their centroids become minimized. However, we know the only distance from between any two vertices according to our consideration. Thus, the second step performs the finding the vertex having the shortest sum of the distance from it to all vertices in the group. On the other hand, K-means clusters have limitation. Different R initial centroid given different partitioning way. Meanwhile, learning all different R initially centroid and R value from 1 to K, the number of output channels consumed the massive amount of time, especially for the layer having an enormous number of AP channels. For example, if a layer has a K output channel, the total number of the causes we need to explore. To reduce the number of cases, we use K-means ++ for initialization for the first R centroid if the number of the search cases is more than 100. In addition to make the output more than correct, all cases the first centroid are executed, and the optimal values is selected instead of randomized for the first centroid. Hence, if one layer has a K output value channels and the number of clusters varies from the 1 to K, the total cases of we execute is K2, K is K square, which is much smaller than the number of test cases of edge K-means algorithm to 2K square, 2K power -1 of K when K is greater than or equal to 5. 3. MHC comparison. To further optimization of MHC operation, which consume the most hardware resources and power consumption in any BNN architecture as shown in the figure 16 and figure 15, we propose applying to two well-known techniques used to do pop count comparison. Firstly, as described in figure 13, the 6 versus 3 comparison versus 6 to 3 comparison is applied to the reduced number of LUTs by using the 6 to 3 types of implement to an adder tree. Each bit of the output result from LSB low significant bit to the MSB most significant bit is sequentially calculated with the adder 6 to 3. 2 kilobits from the adder 63 are stored to calculate more significant output in the end. Doing so, we can avoid using adders with too much and the bit input, leading to the hardware resources reduction. Similarly, the automated hardware implement flow 3-2 compression using the adder 3-2 type is also provided and implemented adder tree as shown in figure 14. Depending on the table 1, hardware resource and power consumption when implementing adder 3 and 3 options, no compression 3-2 and compressor 6-3. Depending on the input bandwidth with the pop count operation, compression 3-2 and compression 6-3 can be selected to implement the adder tree effectively. According to the table 1, our experiment, the compression 3-2 used fewer resources, reduced 7.5% LUTs for the MNIST model and 9.5% LUTs for the Cipher 10, while the compression 6-3 uses less power consumption for both of their sides, 6.7% for MNIST and 11.5% for Cipher 10. In this subsection, we continue to propose another technique called the pop count reuse. The pop reduce to reduce the power-aware resources significantly. More specifically, as shown in Figure 17, without the pop count reuse model, pop count operation are implemented in the K-up channels. While with the pop count reuse, the number of the pop count operation can be reduced x times, in which x is the number of the output channels using the same pop count operations. To maintain the continuity in the streaming architecture, the clock source used for pop count operation is x times faster than the clock source needed for others. The values of x you used based on the required performance and area. When increasing the x value, hardware overhead and performance decrease. By contrast, decreasing x, hardware overhead and performance increase. D. Operation time of the architecture. As discussed in subsection 3.1, the proposed design is coarse-grained pipeline architecture to the number of the pipeline stages, quantifying the number of layers. By overlapping these stages, throughput and the initial pipeline filling are critically improved. In particular, the convolution line buffer of the specific layer starts generating window values after n cycles. Besides applying to the loop only in the pipeline mechanism, the multiplication pop count module requires typical number of clock cycles. Depending on the number of output channels and the input width, the number of clock cycles can be changed to have a highest frequency and matching times constraint. Thus, as shown in figures 18, after nf plus np clock cycles later than the start time of a specific layer, the next layer operation can start. Each pooling layer needs E plus n clock cycles to generate output. In this case, the window size is 2 by 2 and the number of parallel inputs is n. So the next convolution layers needs to wait for E plus n cycles later than the current pooling layer. In terms of the fully connected layer, we also need NFC clock cycles to receive the first data to generating the first temporary maximum values of the 10 output channels. This number of clock cycles can be flexed to change it depending on the required frequency in experience model, which, with the frequency being 300 Hz, the fully connected layer needs the 3 clock cycles to find a maximum value from temporal values of values. Because the input data is continuously filled with the proposed hardware accelerator for BNN, after the initial time latency, each convolution pooling and fully connected layer requires clock cycles to produce one inference operation if the loop 2 does not unload. For the 2 unloading case, the number of required clock cycles can be reduced by n times, and the number of windows and convolution line buffers. Eventually, the number of needs XFN and clock cycles to finish one application for one input image. 4. The experimental result. BNN model exploration. To explore exponential the architecture space and get the optimal BNN models, sometimes the training conditions are required for all models. In particular, in batch room operation is added after each convolutional layer, and the max pooling layer follows batch room operation from the second level convolution layer. For the model using the MNIST dataset, binary search is further used to optimize the number of channels on each layer. The initial inputs are following the training on the MNIST dataset. One is range for the number of layers in the BNN model, L, 3, 4, 5, and the two maximum number of channels per layer, C, 1 less than 50, target accuracy threshold. Based on these input for each L values, we use the binary search to reduce the number of channels of each layers uniformly until a BNN models with the minimum number of channels or layers are found. Next, based on this model, the binary search continued to be used in the minimizing the number of channels for each particular layer. Eventually, the optimum BNN model corresponding to a particular L value is determined, and each model has been a variable number of layers represented by the element of a set. Therefore, the number of output models is represented by the size of the set, but because each initial BNN model is only the number of the channels for each layer is optimized. We independently predefine all of the components of our network's architecture to the reduced search space. Regular the training environment we found a productive optimizer method, then optimizer is the first 30 epochs and a SGD optimizers for remaining 70 epochs. We set the learning rate of the 3.30 and a momentum at the 0.5. For model using the Cipher-10 dataset based on the model structure and sticks, we changed some training condition to make it compatible with our proposed hardware architecture. In particular, we add a padding with the -1 value for each ever convolutional layer to the improve accuracy with a smaller number of channels. In addition, the output feature map of the latest convolution area is guaranteed with one time as one demand, which will override the MAC optimization method on fully connected layers. For training environment, ADAM optimizer is also used with 500 approach the learning rate of 0.005 for the first fully epoch as 10.1 from the 8th epoch, E5 the E5E minus 0.5 from the 120th epoch, and an E5E minus 0.6 from the 106th epoch. In this paper, we aim to find two models for an MNIST dataset using the aforementioned approach. The one model for the Cipher-10 dataset and use them to demonstrate the efficiency of the proposed architecture. First, the MNIST dataset to compare the previous work. In the first model optimization for MNIST, you tried to minimize the BNN models in terms of hardware implementation when we set the target accuracy to the above 98.4% because the other implementation in the previous work support around 98.4%. We call this model MD1. On the other hand, the final highly efficient BNN models in a hardware implementation with reasonable accuracy. We explored many BNN models with different configuration and found an efficient model having a 97.7% accuracy. We call the second model MD2. After doing the architecture search, two series of the optimal models are found for two respective accuracy threshold, 98.4% and 97.7%. In terms of listed models for as 98% according to table 2, the model with the 3 conversion layers, the lowest model number of layers, leading to the lowest difference in latency compared to other models having the same accuracy. In addition, these 3-layer models give the best result in terms of hardware resources. Therefore, this model is chosen and regarded as an MD1 model. Similarly, we also found the MD2 models by exploring many candidates having similar accuracy with the consideration of required hardware resources and corresponding accuracy. In summary, both models have 3 conversion layers and 1 fully connected layer. The MD1 model has 26 models for the first convolution layer, 24 channels for the second layer, and 31 channels for the last convolution layer. And the MD2 model has 17 channels for the first convolution layers, and 15 channels for the second layers, and 22 channels for the first convolution layers. Each convolution layers on both models is followed by the Bachelum functions, and maxipling is applied to the last 2 convolutional layers. Finally, as we discussed in the background section, both models use 16-bit fixed-point pixels and binary weight for the first convolution, and while weight and input feature maps are binarized from the second layers. Second, for the Cipher 10, we get a model on accuracy of 80.2%, where there are 6 convolutional layers, 64, 96, 96, 128, and 192, and 2 fully connected layers, 256 and 10 at the end. Bachelum operation is attached after each layer, and math pooling is added after Bachelum operation from the second to the final convolution layer. B. Automated hardware implementation and verification process. Designing each hardware accelerator for each model is extremely time and effort consuming and error prone process. Based on the idea used in theory, this paper proposed an automated hardware implementation framework to automate the generation of hardware architecture in the register transfer level (RTL) based on the constraint for the BNN model. A script manually generated the RTL design according to the user-specific constraint. In particular, all parameters are separated into 2 sets: modular parameters and general parameters, while the proposed hardware architecture includes the hardware modules specialized for the typical functions such as Bachelum, convolution, line buffer as multiplication, and plus pop count as math pooling, the line buffer, and pooling. To regenerate RTL designs, firstly, the script uses the general parameters set to define a general structure. The coarse-grained architecture, in which an overview of the design is determined by the number of particular modules and their position in the design. Secondly, module parameters set are used to generally configure all input modules and parameters of each typical module at a specific position at the architecture. Finally, this script automatically generates the RTL design by connecting all configured hardware modules. In Figure 19, all parameters in each module are described, and a general parameter set is provided as well. As shown in Figure 20, to verify the operating equivalence of the implemented hardware accelerator with the BNN models in the software implementation, we will verify the multiple accelerator based on the proposed architecture for BNN models with the various layers, channels, and accuracy. First, C and C++ models are constructed based on the parameters and the model structure from the PyTorch models. In particular, each layer in the Python model is built as a C and C++ function. The output of each layer is compared to the respectively between the C and C++ model and the PyTorch models. After having C and C++ models, we prepare a series of C and C++ models corresponding to different numbers of channels and the numbers of layers. And secondly, we implement The perspective hardware accelerated by the automatic script. Then the visual simulation tools from a synopsis used to precisely verify the waveform of each data of the data paths by comparing the result with the corresponding CNC double plus models. Finally, we implemented the accelerators ported into FPGA and verified the operation hardware accelerators with the CNC double plus models. Visual simulation results have been verified bit by the bit and the data path through the integrated logic analyzer ELA provided Xilinx FPGA. By using this automated process, after training the hardware accelerator corresponding the updated software model can be immediately implemented, which is highly desirable the practical application on FPGA. Consequently, manual efforts are eliminated from the hardware design stage to the verification stage for a target application. Experimental implementation. We use automated script to generate RTX description based on the proposed hardware architecture. Input PNN model structure and the user-specific design parameters to evaluate all model functionality. Regarding to the hardware of device, the proposed architecture is implemented in Xilinx Ultra 69 evaluation board, which include an ultra scale MP SoC. In particular, there is a quad-core ARM Cortex-A30 A53 and application processing unit and a dual-core ARM Cortex-R5 real-time processing unit and the processor subsystem PS. And the programmable logic PL part comprises 120 flip-flops and 70,560 lookup tables LUTs. 360 DSP slices and 7.6 megabits block RAM. In addition, is a blah 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 parts including the 522.720 loops and 1,045,044 flip-flops is used to implement the full bigger model. As I mentioned in the previous subsection, we use the synopsis visuals to perform the simulation for the generated RTL design and compare the classification output with the output of the bit through the CW plus for the input BNN models. At the next step, we synthesized and implemented the proposed design by using the Vivado 2018.6.3. All experimental results describe the number of LUTs, flip-flops, estimated power consumptions collected from the Vivado report. Notably, to estimate the power efficiency on the BNN core, we only collected the power consumption and the PR part of the chip. The consistent FPGA logic gate, and we compared the software models and implemented the hardware accelerator bit by bit. While the FPGA bitstream functionality is wholly verified against the data set of 10,000 images. On the PS side, the host C code running on the ARM processor has two tasks. First, each configured and executed directed random access DMA to transfer the test images frame by frame from DRAM to the hardware accelerators and transfer back to the classification result from the hardware accelerator to them. Then after the last result arrives, it compares or receives the classification result with the pre-known output from the C and C double plus model. In Figure 21, the comprehensive system architecture is described in which PS connect to the BNN core for the DMA. A full AS4 bus is used for data transmission between the data controller and the DMA, while the processor manages DMA transmission through the AXI write bus. Figure 21, the system architecture for the testing binary and the neural network IP. D. Experimental evolution. To estimate the efficiency of the proposed architecture, we conducted a list of experiments corresponding to different parameter sets and objectives. In particular, we investigated 5 factors: clock speed, loop to unloading level, MH optimization method, MH conversion method, and classification accuracy. First, we synthesized the MD1 model with different frequency values 1, 1 and 50, 20, at 200, 250, and 300 megahertz. The results show that operating frequency does not affect the hardware sources entirely. In contrast to this, the frame rate or the frame per second increases the power consumption of the hardware implementation. Specifically, according to the figure 22, it was nothing that the FPSW ratio steadily increases among the clock frequency for all loop 2 unrolling levels. This indicated that the proposed architecture, the speed of the image classification increases faster than the rise of power consumption, which leads to the better power efficiency at higher frequencies. Secondly, to study the impact of the loop 2 the unrolling factor, we also synthesized the same MD1 with different values of n, 1, 2, 4, as discussed in the previous session. If the number of proposed windows in each convolutional line buffer increases n times, total system throughput also increases n times. For n equal 1, the accelerator frame rate is 3.83 times 10 to the power of 5, and so it with the N2 and N4 frame rate increases 7.65 times 10.5 and 1.35 times 10 to the 6th power of, respectively. Meanwhile, based on the result table 3, in case n is greater than 1, hardware resources and power consumption increase much less than n times compared to the n1, since both throughput, the power over power, and the throughput over area efficiency are considerably improved. Typically, the number of lookup tables, LUTs, and used MD1 without weight reuse and n1 is 90,211, and while this number for n to n equal to is 28,534, 1.48 times, and M4 is 54,595, 2.8 times. The FFS usage also gives an impressive number when the comparable with the n equal n, being 12,910 and 1.42 times, and 4 to n to 1 and 3 23 23 20 23,080 2.53 times 4 and 4. We also achieved a similar result on MD2, both with and without weight reuse. For power assessment, figure 22 also describes the efficiency enhancement when an increased n value for the MD1 model with the weight reuse enables. According to the chart, the FPSS ratio is doubled when an increase in n from the n2 to 4. Besides, the chart shows the power efficiency with a higher level of parallelism is much better than without changing frequency. Therefore, the proposed architecture can gain the highest efficiency by minimizing the frequency and the parallel level. Figure 22, a power efficiency when the underrolling and the frequency influence. Next, regarding the impact of applying the MH optimizers method, we synthesized both MD1 and MD2 models with and without enabling the way to reuse and run them at 300 megahertz. The result in the table 3 shows the hardware resource and power consumption are significantly reduced when current weights are reused to remove redundant calculation. Generally, with the MAC optimization method, enabling the number of LUTs range from the 53% and 57.6% compared to the no MH optimization for the design, while the number of FF decreased from about 30% and 35%, and the power consumption also decreases approximately from 35% to the 48%, depending on the motor size and the level of the loop unrolling. On the other hand, if the result analyzes along the horizontal direction, same models, different number of windows and particular direction, same levels of n and a different model size, there are two outcomes. The hardware resources Power consumption improvement tend to be higher than the models having more channels, and two, the same tendency appears when this increase in the parallelism level. And in terms of correlation between the MD1 and MD2, the amount of the LUTs used in the MD2, the different values of N is 1.7 and 7 to 1.9 times fewer than the one needed in the MD1, while FF's usage and power consumption are also reduced to 1.3 to 1.5 times and 1.4 to 1.9 times respectively. The classification accuracy only suffers from a slight reduction of 0.7% from the observation. Is necessary to define a practical accuracy level that produces proper efficiency hardware implementation to find an optimal solution. In summary, in Figure 23, a breakdown of all contribution in reducing the area and energy described for the MD1 with the N4. The overall, the lowest resources and energy reduction by the MAC optimization method, weight reuse much more than the other contribution, with a 67.56% and 74.8% added 39.11% for LUTs, FFs, and power respectively. Meanwhile, the MH compression method gained the lowest effective, which resources LUTs and flip-flops and experience with 6.31% and 1% reduction for the LUTs and FFs respectively. Regarding pipeline unrolling, with the N4 and reduction under these techniques account for the 26.12% LUTs, 24.24% flip-flops, and 3.45% power. So after all the investigation, we can conclude the proposed architecture can be utilized most effectively by learning the highest frequency and the parallel level, in addition to maximize the number of channels on each layer is compatible with the trade-offs to keep the accuracy instead of changing other factors. Comparison to the prior work. In this subsection, we continue comparing the most reliable result of the proposed architecture and the previous work using the MNIST and the CIFAR 10 dataset. For the MNIST dataset, the table for the model MD1 and MD2 implemented with the MAC optimization method, popcorn comparison or without a popcorn comparison are selected to compare with the previous work, in which there are 4 MD1 with 2 and 4 windows and 2 MD2 with the 4 windows. Based on the result at 300 MHz, the popcorn compression method can make the design smaller with a lower number of LUTs and flip-flops. However, the power consumption is more than using the pop count without a compression. The energy interface between the using pop count compression and not using pop count compression is reduced with a lower frequency or a bigger motor, as shown in the figure table 1. We chose the 5 architectures that provide a competitive performance using the MNIST dataset and binary weight regarding previous rules. Firstly, authors in FIN implemented a family of BNN models on the hardware. They implemented an MLP model which comprised 3 fully connected layers, takes a 28 times 28 binary image as an input. Among the previous work, FINN has the highest speed of the image classification of MNIST dataset, 1561 kilo FPS, and the second reference named the FINN-R is also an MLP model proposed by the Xilinx research team. This model gives a low power the consumption much lower than the hardware resources B, N, N, P, Y, and Q. The latest release of the FINN from the Xilinx open source project published on GitHub. So we downloaded the project and synthesized it to reproduce their hardware utilization for comparison. This model has the same accuracy in the FINN, but the architecture consists of 4 fully connected layers. In addition to compared to the FINN, this model uses considerably lower resources but provided a much lower performance. FPS 56.6 kilo fps. The model in the FBPIN paper also used for fully connected layers to classify the MNIST dataset. The difference in this paper is that they used the static V5 from the Altera Intel. They suggest the compressor tree to optimize the pop count operation. The final reference is RBBNet, which is a proposed version of FINN combined with the algorithm optimization. This model shows its efficiency when keeping accuracy at 98.29% while requiring the hardware resources like 25,600 LUTs, being much smaller than the original FINN. The table 4 shows the whole configuration's hardware implementation result of all references and two our models. The hardware implementation based on the proposed architecture provide minimal area compared to other prior works regarding hardware utilization for P, N, P, Y, and Q, including the most lightweight architecture among the previous work from the Xilinx, and our MD1 with two windows consumed 1.84 times fewer LUTs and 3.77 times fewer FFS, and provided 2.14 higher framework rate and 1.36 lower power consumption. Even for Windows generation, our model MD1 used for fewer resources than a BN, PI, and Q with more LUT with a little more LUTs count and 2.1 times fewer flip-flops, but still produce 4.3 and a higher frame rate while maintaining the same accuracy. When compared to with the original FINN and MD1 with 4 windows used 3.3 times fewer LUTs and proposed 98% frame rate. On the other hand, the smaller models M2 provided a modest accuracy with the PINNR, but used 2.4 times fewer than LUTs and provided 1.88 times higher frame rate when operating at the same clock speed. Unlike all other architecture, both MD1 and MD2 completely eliminated the use of the on-chip memory devices and DSP slices, thus improving substantially power consumption. As discussed in the previous section, the power efficiency of our architecture becomes maximized, and when the increasing the both clock speed and the loop unload level at 300 MHz and M4, MD1, MD2 with 4 Windows generation provided 3.8 times and 6.1 times higher FPS FPS per W compared to the BNN, PN, PY, and Q respectively. Although not listed in all table 4, both of our models can be configured with the lower values of N if the frame rate is not prioritized as hardware resources. For the Cipher 10 dataset, we present 4 different architectures with different X values. With the X1 values, proposed architecture is implemented at 2010 and 2010 and 177 MHz. Based on the result, we can conclude the area efficiency increased if the design is run at maximum frequency at X2. The frequency used for MHC operation is 300 MHz, while the rest is run is 150 MHz compared to the case X1. The number of LUTs decreases from the 80% to the 20%. At X4, MS operation continues running at 300 MHz and 75 MHz for others. Hardware overhead ledger 32% and 46% compared to the X2 and X1 respectively. To evaluate the hard area efficiency, according to table 5, the ratio of the FPS per LUTs is used to compare between the proposed design and the remarkable previous works. The proposed design gives all X values better than efficiency and all previous design. In particular, the proposed design and area efficiency with X1 as 0.707 is 1.5 times higher than the best previous design 16. Regarding the performance, the proposed design can give a super fast frame rate with 205,000 frames per second. In summary, based on the result table 4 and 5, Table 4 and 5. Table 5 proposed design for both MNIST and the Cipher-10 data set gives significantly higher power and area efficiency than a previous work. The main reason is from successfully applying some new optimization method based on streaming and binary architecture features, and particularly firstly different from the previous works, which are compared to a table 4 and 5, or XNOR logic gate into the design are removed or replaced by a NOT gate smaller than an XNOR. As a consequence, memory storing weight counter values eliminated. Therefore, internal memory of the proposed design is 0, as shown in Table 4, while the 6, 12, 16, 32, 37, 33 need a certain amount of memory, VRAM. Secondly, the image operation method is directly implemented without additional resources compared to 18. In addition to the line buffer in the proposed design, just store necessary data to provide the next layer instead of storing all output feature maps. Hence, the resources used for the proposed design are much lower than our previous work. Moreover, the pipeline or rolling method of MyJudge utilizes of the max pooling layer with the line buffer supporting the various parallel levels leading to the best power to resource efficiency. The throughput can increase n times while the required hardware overhead is much more than n times. Finally, the MS compression techniques measured in the section 3C3 as the last feature that has proposed design reduce a considerable amount of the hardware resources without a performance impact. A formal numerous data set according to the data region MNIST to Cipher-10 data set, we can see that the area power and performance efficiency can be changed depending on the compression level of the image operation. In particular, the increase in the n values, number of generated windows from the line buffers, or area power consumption or the throughput increases, where the throughput rises faster than the rest. Hence, the energy and the area efficiency is improved. Meanwhile, the increasing x values number of output channels using the one pop count operation, or area frequency and energy and the throughput decrease in which the throughput decreases faster than the rest, causing the efficiency of all aspects to be lower. In conclusion, the area, energy, and the performance efficiency of a specific design using the proposed architecture depending on the x and x values, while x and values on the available resources. Similarly, the wide complex data set ImageNet BNN has found it challenging to have a compatible accuracy for the particular applications, 41% in 33. In addition, currently, because of the lack of the previous work implementing PNN for the ImageNet dataset, the more entire evaluate the proposed architecture of a larger networks with complex data set, the corresponding the proposed architecture are going to be implemented in the future work. Because the proposed architecture focused on the compressing the model with the avoided obstacles caused by the large number of layers, FPGA devices with much more hardware resources and ASICs are going to be used to implement larger models with the complex data sets. Moreover, to maintain the acceptable accuracy of the particular application, increased width should be considered rather than increase the depth when the training larger BNN models. The conclusion: the BNN with the small size parameters and the low cost calculation is a perfect fit to the implemented for the intent of the things or edge application. Various optimization techniques have been cooperate with the proposed design both from the hardware algorithm point of view. The streaming architecture and unrolling mechanism enables a high processing throughput, while the VRAM-less architecture and the reuse method significantly reduce both hardware resources and power consumption in the final routed implementation. The effect of the different optimization approach has been normalized to provide a reference, which is the optimized set of the set of parameters, design parameters for a particular design goal. In addition, they represented a automated design generation flow to implement the arbitrary BNN models onto FPGA based on user-specified BNN structures to optimize the throughput, minimize the power consumption to practical development time. As of date, the proposed PNN implementation delivered the highest performance in terms of throughput and power efficiency without sacrificing increased inference accuracy. In future work to increase the application range, the proposed architecture will continue to remove the more complex neural network models, including the shortcut connection with a small area and low latency. The proposed design is one of the best candidates for IoT or edge application, where low power consumption and real-time response are of the essence. Reference. Okay, thank you for your time for the leading this paper. They are deep learning accelerator based on a streaming architecture for binary neural networks. This is the IEEE access. Okay, thank you again.